Welcome to the fourth video in a series of 5 on linear regression, the regression line, also known as the line of best fit. Here's a situation. Suppose we were analyzing a correlation between a person's height in inches and their shoe size. Suppose we gathered all the data. Here's a plot of the data to give you a better sense of what it represents. And each dot on this scatter plot represents one person and their height and their shoe size. So at this point, hit pause, enter the data in your calculator, and let's see if we get the same results. When you did linear regression on your calculator, you should have gotten numbers somewhat like these. Now they will look a little different because I round to 3 significant figures and the calculator rounds way further than that. But roughly this is what you should have. Okay, let's talk about interpolation and what that is in a linear regression sense. Interpolation is essentially making a prediction about the population from which these data came. For example, what would we expect for the shoe size of someone who is 65 inches tall? Well, why should this even be a mathematical calculation? We have a person in our data set who was 65 inches tall and they had a shoe size of 7. Great, but this is just one individual. And we're trying to take this data and extend it to a much larger population. Maybe this person is significantly above or below average compared to other 65-inch tall people in the population. So when we ask questions like, what would we expect for the shoe size of someone who's 65 inches tall, we're not really looking at our specific small data set. We're really asking a question about the population. Well, how would we go about doing that if we don't have any other information from the population at large? Well, it turns out we can take the A and the B from the linear regression screen in our calculator and use those to make some sense out of the population as a whole. Here's how. Your calculator refers to the line as y equals ax plus b. In this particular case, we have specific values for A and B. Now let's not forget that y and x are just the mathematical letters that represent the shoe size and the height in this particular case. So I've rewritten my equation using words so I can track this a little bit better. Now one thing I could do with this equation is I could graph it. And if I did, I've done that for you, and it ends up being this line here superimposed over the scatter plot. Now, one thing that's interesting to me is that that line, in some general sense, tracks the data we have. We call this the line of best fit because in some technical mathematical way, which we will not discuss in this video, that is the best one-line approximation that gets as close as possible to all the data. What does that actually mean? This video does not cover that. It's a fascinating question. But moving on, there we have our line of best fit, also known as the regression line given to us by the calculator. So back to the question, what could we expect in general for shoe size among all 65-inch tall people in this population? Well, one way to do this is to use the graph. Here's 65 inches. We could go up to the linear regression line and over, and it looks just on the appearance here that we would expect, on average, 65-inch tall people would have a shoe size averaging around 9. Now, you don't want to necessarily rely on a graph. It's often better sometimes to do the algebra. So what I can do is I can take my y equals ax plus b equation that I've developed here at the bottom of the screen, and I can plug in 65 for height, which essentially is the question I'm asked to interpolate. And if you want to pause and see the algebra, you can. The algebra shows that we would expect a shoe size of 9.3 on average among 65-inch tall people in this population. Now, you can't go to the store and buy a shoe size of 9.3. We're not saying that that's the case, but that would be the average that we would expect among all 65-inch tall people. Let's examine something called extrapolation. Extrapolation answers similar questions. You'll notice this is almost identical to the previous question with a different number. But extrapolation asks us to go beyond the numbers given in the data. Notice the tallest person in our data set is 75 inches tall, yet this question is about a 77-inch tall person. So they're beyond the bounds of our data. Well, let's do the math here. Here's where 77 would be. If I were to go up to the regression line, and notice I stopped right about where the regression line would meet and went over, it looks to be that I might extrapolate that a 77-inch tall person might have a shoe size, or we would expect an average shoe size of 16. Now we could also use the equation to do the algebra here. I've plugged in 77 for height and done the algebra, and I did in fact get something very close to 16. So what can we conclude? Absolutely nothing. It's not to say that this is wrong, but the further you go beyond your data set, the further out you extrapolate, the less likely you are to be right. And as a general rule, we don't extrapolate using linear regression. Now, it's a much broader statistical question. When can you expect accuracy upon extrapolation? That's for another time and place and won't be discussed in this video. Let's talk about the word residual. Residual is a measurement for one particular element of your data called a datum, and it's a measurement of how far above or below that one y value, or in this case shoe size, varies from what we would expect it to population-wide. Now that's a very general statement. I think it'll make more sense when you see an example. Let's take this one person as an example. We mentioned them earlier. They're 65 inches tall and they have a shoe size of 7. Now based on the dotted green regression line that you see, it looks like that one individual is below what we would expect a 65-inch person's shoe size to be. After all, they have a shoe size of 7. We saw earlier that we would expect a shoe size of 9.3 population-wide average for 65-inch tall people. Remember the math here? And so what that shows me is that this person is 2.3 shoe sizes lower than a regression equation would predict for that particular height. And since the residual is how much above or below expectation one individual data point is, we would say that that person, or that datum in this case, has a residual of negative 2.3. Negative because they're below expectation, and 2.3 is how far below the regression line they are. Take a look at the graph briefly. This distance here represents how far below the expected group average for 65-inch tall people that person would be in terms of shoe size, and so that line segment, or the length of it, represents their residual. Let's take a look at a second example here. Let's examine the impact of the number of hours of TV watched on a particular midterm. Here we have a handful of people. We've recorded the number of TV hours that they watched, say in the week leading up to the midterm, and we have their actual midterm scores. So is there a correlation between these two variables? And if so, what predictions can we make about them? Here's the data represented in a scatter plot. As usual, that helps to see it. Reach for your calculator, pause the video, and find the regression line corresponding to this data. Okay, you should have gotten these numbers in your calculator. Again, I round differently than your calculator does. Neither one of us is right, more right than the other, but this is my style. Okay, let's go to interpolation again and get a sense of how that can be used. Interpolation is the process by which we use the regression line to make a prediction about the population beyond the small data set that we have. In other words, we can answer questions like this. What would we expect about the number of hours of TV among people who scored 60 on the midterm? Let's say we had tons and tons of students who had taken this midterm over the years, and we gathered together all the people who scored 60 on it, and we wanted to make some generalization about how much TV they might have watched. Now, there's no way to do that for one individual. Statistics doesn't do that. But we can make a generalization about all people who scored 60 on the midterm based on this data. So, how do we do that? Again, we take our A and our B from our linear regression screen on our calculator. We make an equation out of it. And I like to write in what y and x represent. It kind of keeps me grounded. If I'm just working with x's and y's, I tend to forget what they mean. Okay, now we can use this equation as an interpolation. First, we could graph this equation. You see it as the dotted green line superimposed over the data. Again, we call this the line of best fit. It doesn't really seem to hit many of the data points, you'll notice. Maybe 2 of them at most. But lines of best fit are not meant to hit individual data points. They're supposed to be the best overall representation of the data that we can make based on a handful of information. Okay, where does this line come from? Well, it comes from your calculator. How does your calculator know how to do that? That's a great question that this video does not cover, but it's actually interesting. There's a mathematical way of making the line, quote, as close as possible to all the points. What does that actually mean? That's a discussion for another time and day. Okay, now back to our interpolation about the people who scored 60 on the midterm in this population. We could say, well, here's 60. If we look over at the regression line and go down, a 60 on the midterm seems to correlate in some sense to maybe 12 hours of television. By the way, I'm not sure that that's necessarily is a super strong correlation. You'll notice the correlation coefficient is negative 0.53. That's not, I wouldn't call that an extraordinarily high correlation, but nonetheless, our prediction is maybe 12 hours of TV for this group of people. But of course, we don't want to rely on the graph when we can use algebra. So what I've done here, notice the purple, I've plugged in 60 for the midterm score in my equation. And I, on scratch paper, and I did not show it in this video, but I used scratch paper and solved for the TV hours. If this looks weird to you, don't panic. It's 7th grade algebra. It's very easy. And you could pause the video and do it yourself and be convinced how simple that was. But that tells me that I expect among the people who scored 60 on the midterm that they may have averaged 11.3 hours of TV. Okay. Let's talk residual. Let's look at the Well, remember, residual is comparing one individual point of data. By the way, datum is just singular for the word data. Data is plural, just in case you didn't know. Moving on, a residual is where we look at one individual data point, or in this case, person, and analyze whether they scored above or below the expectation and by how much. Let's look at this unusual person here. This person spent 12 hours watching TV and yet managed to score an 84 on the midterm. And just by that point's location on the graph by itself, it does appear to be quite above what we would expect compared to other people who scored 12 on the midterm. And I don't mean the two other people I don't mean the two other people who spent 12 hours watching TV. I mean, how did they compare in relation to all the people in the population, including the ones we don't know but we're making predictions about, who spent 12 hours watching TV? So to compute the residual, you just have to know what the person's Y value or midterm score was. In this case, of course, they got an 84 on the midterm. But among people who watch 12 hours of TV, we could do some algebra here. Hit pause if you need to analyze the algebra more. But I've plugged in 12 for TV hours in my equation and determined that we would expect the group of people who watched 12 hours of TV to have scored on average 59 on the midterm. And that's right here on my y-axis. So how much better is 84 than 59? Well, I subtracted on scratch paper, and I found out that this person scored 25 points higher than would be expected among those who watched 12 hours of TV. And so we say that that person's residual is positive 25. And take a look at the graph. It represents the distance, in this case above the regression line. Well, those were the two examples, but let's take a look at a couple additional items in relation to the two examples we've seen before we wrap up this video. More thoughts. Earlier, we looked at height and shoe size, and we looked at TV hours and midterm scores, and we looked for correlations between them. First, I'd like to point out that the correlation coefficient for the height shoe size problem was higher than the correlation coefficient for the TV and midterm problem. And I don't mean higher because it's a positive number and positive numbers are higher than negative numbers. I mean in actual absolute value, 0.78 is bigger than 0.53. So there seems to be a higher correlation there. I would say that the predictions we made about shoe size are much more likely to be true population-wide than the predictions we made about midterm scores. Now let's also take a look at this A value. This A is a very important number, and you've seen me use it in the math problems, but we haven't really talked about what it means. Let's recall that y equals ax plus b is our regression equation or line of best fit, so a is the coefficient of x. But I think we all remember y equals mx plus b from other math courses, where m is the slope of the line and b is the y-intercept. Hopefully you remember that. In any case, m is just the letter that represents slope in an algebra class. A is the letter that represents slope in most statistics courses. Why the change of letters? Long history behind that, but let's face facts. Calling the slope by a different letter doesn't change what it means. Now, your algebra teacher in the past may or may not have told you the meaning of slope. Here it is. This is the definition of slope and often gets lost in an algebra class because slope ends up being rise over run, because thinking of it that way is is uniquely helpful for graphing situations, but this is the real meaning of slope. As one variable increases by 1, the input variable that is, how much increase or decrease is there in the output variable? That's the real meaning of slope. Now let's take that idea and interpret what that would mean in the height shoe size problem and in the TV hour midterm problem. First, the height shoe size. In that problem, we have a slope of 0.551. Here's the interpretation. I'll be quiet while you read. That statement and the purple statement above it are exactly the same statement. If you think about it long enough, you'll see that. So the interpretation of the slope of 0.551 is for each additional 1 inch in height from one person to the next, we would expect an increase in shoe size of 0.551, or roughly half a size. So as a generalization, if we had 2 people and one were an inch taller than the other, we would expect them to have a half shoe size more. But of course, that's not always the case, and statistics doesn't make representations about individual people. It's really more about the group. Now let's look at the TV hour and midterm problem. There the slope was negative 1.4. Here's the interpretation of that. Here, because the slope is negative, we would expect an increase in x would lead to a decrease in y, meaning an increase in TV hours watched would lead to a decrease in midterm score, on average by 1.42 points for each additional hour of TV watched. And that completes the 4th of 5 lessons.